Hey everyone. In the last episode, we defined probability. We determined the framework in which we will consider any probability problem. Everything that we study in probability from this moment on will be described by this framework. I will repeat it now, and you probably are tired of me repeating this for the third time, but it is important because this framework will be behind the curtains from now on. We'll not mention it, but you should be able to get back to it whenever needed. This framework is very important. We're conducting an experiment. The set of all outcomes is called the sample space. And is usually denoted capital S as opposed to little s that denotes the outcome. Any subset of the sample space, in other words, any collection of outcomes, is called an event. Probability is an assignment of a positive number to every event. That number measures the likelihood of that event. Not every assignment is valid, and we require the probability to satisfy the three main properties. These properties are part of definition, and therefore it's convenient to call them axioms. First, the probability of any event is a non-negative number. Second, the probability of the entire sample space, probability that some outcome happens, is always 1. And the third axiom is called the additivity axiom. It says that if we decompose an event E into mutually exclusive events, then we can compute the probability of E by summing the probabilities of its parts. For any mutually exclusive events, E1 through En, the probability of their union equals the sum of their probabilities. This definition does not tell us how to find probability, how to make that assignment. In fact, many assignments are possible, and the simplest assignment that we considered last time is the uniform probability, in which any outcome is equally likely. Any outcome that can happen has the same probability. In this case, the probability of any event is proportional to the number of elements in it. So the probability can be computed using this formula. This is the basic framework of probability theory. Today, we'll draw some simple consequences from these axioms. The first proposition allows us to compute probabilities by passing to the complement, a very useful trick. It says that for any event E, the probability that E does not happen, and that is indicated by the complement to E, can be computed by subtracting from 1 the probability that E happens. This is a sample space. Let's say this is E right here, and the rest is the complement over here. To see why this formula holds, we can just think of the sample space S as the union of E and E complement. Obviously, E and E complement are mutually exclusive. There is no outcome that can be both an E and E complement. Therefore, the additivity axiom says that the probability of S equals probability of E plus probability of E complement, because we just decomposed this set into 2 mutually exclusive events. The probability of S from axiom 2 equals 1. And then just rearrange the terms in this equation to get this. We proved this formula. As a corollary, we can compute the probability of the empty set, the event that does not have any outcome. What do you think it should be? Probability that nothing happens at all, that no outcome happens. Well, it can't be. The experiment must result in some outcome. So something must always happen, and that probability should be equal to 0. Let's see that formally. The empty set is the complement to the full set. Remember, the complement contains all the outcomes that are not in S. S contains all of them, so the complement to S is just the empty set. Now we are applying this formula, this time for E being S, and we get that this is 1 minus P of S. By axiom 2, P of S equals 1, and this is 1 minus 1, and we get a 0. We just showed that the probability of the empty event is 0, as we predicted. Not a big surprise here, right? Another natural consequence is monotonicity. If event E implies event F, think of E being smaller and F being a larger event, then the probability of E is less than or equal to the probability of F. Why is this true? Suppose this is our event F, and this is our event E, it's smaller. The outcomes that are outside E but are still in F, they form the event F set minus E. Indeed, the definition of the set minus operation makes F minus E consist of all outcomes that are included in F but are excluded from E. F breaks down into the union of E and F set minus E. And these two events are mutually exclusive. Check this more formally. So the additivity axiom states that the probability of F equals probability of E plus the probability of that. The probability is always non-negative by axiom 1. And that means that this expression is greater or equal to P of E. And we proved P of F is larger than P of E. A consequence to this proposition is that the probability of any event E is at most 1. Indeed, E is always included in the sample space, and the probability of the sample space is 1 by axiom 2. So if we just apply the monotonicity property, we get that P of E is less than 1. This means that probability of every event is between 0 by axiom 1 and 1 by this corollary. So now let's solve this exercise. Suppose the Ministry of Propaganda publishes 99 genuine, true news and 1 fake news every day. An independent fact-checking agency checks the authenticity of 1 randomly chosen news story every day. What's the probability that the ministry's dishonesty gets exposed by 100th day? In other words, what's the probability that the fact-checking agency stumbles on at least 1 fake news in the first 100 days? So here's day 1, and in day 1, there are 99 genuine news and 1 fake. This is similarly day 2, 99 genuine and 1 fake. And there are 100 days on each of which the ministry publishes 99 genuine news stories and 1 fake. Let's formulate this problem in the framework of probability that we just described. The experiment is to check one news every day. So in this experiment, we draw one news from the set of 100 news published by the ministry on each of the days. Select one story every day. That's our experiment. An outcome is just a collection of these stories, one per day. The set of all outcomes are all possible combinations, all possible ways to select one story from the 100 stories every day. We can assume that all outcomes are equally likely. And that is because the fact-checking agency does not know beforehand what story it will check. It just checks completely at random every day. That assumption makes the probability assignment a uniform probability, and the probability of any event of interest can be then computed using just by the ratio of the number of outcomes in E over the total number of outcomes. How many outcomes does S have? How many ways are there to select one story every day? On the first day, there are 100 ways to select one story. Any story of this 100 is okay. The second day is 100, the third day, and so on and so forth, and the last day is still where we can select one of the 100 stories. So this number, 100 to 100, that is the size of the sample space. Our event, the event of interest to us, is that the ministry's dishonesty gets exposed by the 100th day, less denoted by E. To compute the probability of E, it is simpler to pass to the complement. How do we know? Well, we don't. Try to do it directly. And you will see that it is actually difficult because you do not know which day the ministry will get exposed. There are many. However, if we pass to the complement to this event is that the dishonesty of the ministry will not get exposed by 100th day. That means that on each of these days, a genuine news story is selected by the fact-checking agency. That is the way the ministry is not get caught, because every day, just by accident, we check the true story and we say, okay. So E, complement, then consists of all possible ways to select one genuine story for each of the 100 days. What is the size of E complement? How many ways are there to select one genuine story every day? On day one, there are 99 ways because there are 99 genuine stories. On day two, there are another 99 and so on and so forth. So by the multiplication principle, there are this many ways to select one genuine story every day. So we computed both the sizes of E complement and the size of S, because probability is uniform in our situation. It is computed as a fraction like this. So it's 99 to 100 over 100 to 100. I can put this in the calculator, but isn't this something similar to what we did before? Isn't this familiar to you? The classical limit, 1 minus 1 over n to the power of n. As n goes to infinity, this number converges to 1 over e. If there was a plus here, the number would be e. So the probability here is approximately 1 over e. And applying the complement rule, we can compute the probability of the original event by subtracting this from 1. And we get 1 minus 1 over e, which is approximately 0.63. And that is the answer. With probability around 63%, the Ministry of Propaganda will get caught by the 100th day. Thank you for staying with me. this project is completely voluntary, and I don't get any benefit from it other than knowing that you're getting a quality introduction to probability theory. So please put a like on this and other videos. Thank you, and stay with me for the next episode.